So remember that last week we started looking at vectors. We looked at vectors with initial and terminal points. We looked at graphing them. We looked at finding magnitudes and putting them in component form. And then we looked at adding and subtracting them. So today we're going to do just a couple more things with them. The first thing is, remember last week we talked about our zero vector, which what did our zero vector have? So a zero vector specifically had a, well, what did we use instead of length? A magnitude of 0, okay? So what do we think a unit vector might have? A what of 1? A magnitude of 1. So a unit vector is something that has a magnitude of 1. And remember that our magnitude symbol looks like two absolute value signs, which we need to know what that means. Because I could say, find the magnitude of u, or I could just say find, and then put the two little absolute value things. So you need to know that they mean the same thing. Okay? Now, we do also have two special unit vectors, and they are I and j. So unit vector I is the vector 1, 0, and unit vector j is 0, 1. Now notice that if I found the magnitude of each of those, it would be the square root of 1 squared plus 0 squared. So we do get 1, which is why they're both unit vectors. And we can use these to kind of put our vectors in a different form. So remember last week we looked at component form, which is what both of our I and j are in. But we can also rewrite vectors as linear combinations, which is just kind of another format to put them in. So if I have, say, u equals u1, comma, u2, notice that my I only has an x component and my j only has a y component. So basically we're going to take each of those components and put them next to either the I or the j. So this would look like u1 times vector I plus u2 times vector j. So again, it's just kind of another way to rewrite out. U sub 1 times I plus U sub 2 times j. Questions on that? So far? So good? Alright, let's look at an example. So it says let u be the vector with the initial point 2, -5 and the terminal point -1, 3. Write u as a linear combination of the standard unit vectors I and j. Basically it's just asking us to do what I just wrote on the previous page. Now notice that what format is u in when I use my definition? Component form, right? So we need to write u in component form before we can write it in linear combination form. Does that make sense? Yeah. So how do we put things in component form? Oh, excuse me. So remember from last week, what is component form? Yes. So which one do I get for the second one? No, like, which one of my points is the 2's? Like, how do I know which one?
Oh, the terminal.
The terminal point. So remember, we want to do terminal minus initial. And then, yes, we're breaking it into x's and y's. So we would have -1 minus 2, comma, 3 minus -5. So what do we get?
-3.
Comma.
8.
So now, if we wanted to rewrite that as a linear combination, like I said, all we're going to do is take our x component, which is -3, and stick that in front of our I. Take our y component, which is 8, and stick that in front of our j. And that's our answer. And it kind of just depends on like what you're doing with the vectors, like which one or which format you would want it in. So sometimes component form works. A lot of times when we're dealing with like multiple vectors and you're trying to like add or subtract or stuff like that with them, we'll leave it in the linear combination form because it's a little bit easier to work with.
This iron day.
Correct. Whatever is our x goes with I. Whatever's with our y. Alrighty. So now, like I said, the reason that we can use these is if we're trying to add or subtract them, sometimes it's helpful for them to be in this format. And basically, we can kind of treat them as variables, basically. So if we're looking for 2u minus 3b, it's going to be like our normal order of operations. I need to do our scalar multiplication first. And then we will subtract. So if I multiply each of my pieces by 2 on u, what do we end up with? -6i plus
16.
j. And then if I multiply each of my second pieces by 3, what do we end up with?
-6i plus 3j.
And we're just doing the 3, not the minus. Okay, so then I'm subtracting. So -6i minus 6i gives us and then 16j minus a -3j gives us 19j. And that's my answer. And generally, if they give it to us in linear combination form, we're going to leave it in linear combination form as our answer. Unless they said, like, and write it in component form. But if they don't tell us, then we're just going to leave it in whatever form they gave it to us in. Questions on that? Yes. Okay. So, we talked about addition and subtraction, but we also have what's called dot products. So it's kind of like multiplication for vectors, but it's not quite. Like I can't just multiply the parts like we did with the addition and subtraction. So if I have that u equals u1 comma u2 and v equals v1 comma v2, then if I do u dot v, it's going to equal u1 times v1 plus u2 times v2. And notice that that is just going to be a number or a scalar. So dot products do not give us vectors. So dot products equal scalars. I'm just going to get a number. Scalar is just a number. It's something that has magnitude but no direction. So it's another way of saying a constant. So then we have some properties with our dot product. So since our dot product is defined as things with multiplication and addition, both of those are commutative, which means that dot product ing is also commutative. So u dot v is the same thing as v dot u. Also, if I multiply a vector by the zero vector, I will get 0. We can also kind of think about it like distributing. So we are allowed to distribute dot products within addition. Something dot product with itself is its magnitude squared. And then if we have scalar multiplication, we can either do the dot product first and then multiply by the scalar, or we can multiply the scalar to one of our vectors and then dot product. Either way. So let's look at an example. So it says find each dot product. Now, what are our answers going to be for our dot products? Scalars. So I'm just going to get a number. So notice like on A, okay, I'm going to do my x components, so 4 times 2, and then I add my y components, so 5 times 3. So we get
15.
8 plus 15, which gives us 23. And that's our answer. Because these aren't points, they're vectors. So they use a different notation so that way you can tell the difference just between a point and then something that's actually a vector. Sometimes in some of your science classes you can also see vectors written kind of like a matrix, but it's not as common of notation for math. So then on our next one, what are my x components? 2 and 1, and then my y components. Okay, so what do we get? So we get 0, which is fine. Sometimes we're going to end up with 0. Alright, and then lastly, our x components and our y components. So we get 0 plus a negative 6 gives us negative. Okay. And those are dot products. Yay. So So the last thing that we can kind of look at, like I said, we can use our properties with our dot products, okay? So on our first one, notice that we have parentheses, so we kind of want to treat your vectors just like we do with normal order of operations. We want to do our parentheses first, okay? Now, let's think, what type of answer is A going to be? A vector or a scalar? You sure?
Oh, no.
So U dot V will give us a scalar, but then if I multiply that scalar with vector W, that would give me a vector. So they're kind of going to repeat themselves. So if I just dot product two vectors together, I get a scalar. If I multiply or dot product 3, I'm going to get a vector. 4 scalar, 5 vectors. It's just kind of repeat itself. So yes. So here I want to do my U dot V first. So U dot V. What are my X components? -1 and 2. And then I'm going to add 3 times -4. So we get -2 plus a -12, which is -14. So then if I want to find U dot V times W, now I just have -14 times W. So what do I do when I just have a scalar?
You multiply by each one.
We distribute, basically multiply it by each component. So we would get -14, comma, +28. And that would be my answer. Now, notice on part B, okay, we have U dot 2V. So we could multiply my 2 by my V and then dot product those two things. However, remember back to our properties, if I have a constant with one of my vectors, we're also allowed to do our dot product first and then multiply by that constant. Because notice, if I do it in that order, we basically lose a step because we already have U dot V. Yes? We already found that? So we don't have to do as much work. Basically, we're just going to do 2 times -14 now, which gives us -28. So that's why sometimes our properties can make our lives a little bit easier if we already have some information that we can use. Questions on that? Yeah.
I'm confused after -14.
Which one?
The W part.
This one?
Yeah.
So remember we talked about on Friday scalar multiplication. If I multiply a scalar, so -14 is just a number. If I multiply a scalar by a vector, we just distribute that number to each of the components in our vector. So like -14 times 1 is -14. -14 times -2 is a +28. Other questions? Now, this is in our trig unit, and we haven't done a ton of trig stuff with this. There are a couple of different trig things that we can do. So remember we talked about technically our magnitude is the distance formula, which we get by the Pythagorean theorem. And then the other thing that we're going to look at is we can also find the angle between two vectors using a cosine. Now, there are some other more advanced things that you can do with vectors, but we're not going to get into them in this class. But if you continued on into some higher level science classes, they they would teach you the stuff that you need to know about the vectors in those classes. We're kind of just looking at a brief overview of what you can do with vectors. So on top we have u dot v. On bottom we have the magnitude of u times the magnitude of v. And that equals cosine of theta. So let's look at my example of that. Alright, so let's find the angle between u, which is 4, 3, and v, which is 3, 5, and they give us a nice pretty picture. Now the picture isn't necessary, I can still use the formula without the picture. However, the picture is nice because from our picture, what do we know our theta has to be? What's that the angle? Has to be an acute angle. So that's a good way for me to check myself. Like if I end up with 112, right, we did something wrong. Because both of these are in my first quadrant, which means there's no way for me to get something larger than 90 degrees. Okay? So remember that our formula is cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. Now, you can just try and plug all of those formulas in at once, but I think it's usually a little bit easier to kind of come off to the side, find our u dot v, find our magnitude of u, find our magnitude of v, and then plug those things in. Does that make sense? Otherwise, you end up with a lot of formulas all in one. So if we wanted to find u dot v, what is our x components?
4 times 3.
And then I'm going to add our y components.
3 times 5.
Okay, so we get,
12 plus 15.
which gives us,
27.
yay, so 1 down. Now, remind me, when I have things in component form, how do I find our magnitude? Remember, our magnitude is just the length of our vector, which we can find using our distance formula. And remember, normally our distance formula is like our x2 minus x1 and our y2 minus y1. But remember that if it's given in component form, basically we've already taken care of that because our initial point is at 0. So remember, we're just going to take our x component and square it plus our y component squared. I take the square root. So 4 squared gives us 16, 3 squared gives us 9, so we get the square root of 25, which is also 5. Read? Yes? No? Maybe? Okay, so then our last thing, we need to find the magnitude of v, which is going to be the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25, which is the square root of 34. Can I simplify the square root of 34?
No.
Nope. It's going to be 2 times 17, right? And that doesn't reduce. So that's just how we're going to leave it, which is okay. We don't have to have exact things. Sometimes we might end up with exact things to where we could use our unit circle, but it's not a requirement. So I'm just plugging those numbers into my formula. So then how would I solve for theta?
Do inverse cosine.
So cosine, inverse of that stuff, and then I'm going to plug it into our calculator, and what do we get?
22.6.
Which makes sense because we said that it's going to have to be an acute angle, and this angle doesn't even take up half of that quadrant, so we know it should at least be less than 45 as well, which 22 is, so our answer makes sense. Questions on that? So now you can try one last one on your own. They should get a much nicer number for this one.
It's a kid. Everything's fun.
So what we get?
45.
divided by the magnitude of u times the magnitude of v. So u dot v this time is 2 times 1 plus 1 times 3, which is also 5. My magnitude of u is the square root of 2 squared plus 1 squared, which is also the square root of 5. My magnitude of v is the square root of 1 squared plus 3 squared, which is the square root of 10. So then I'm plugging all of those things. My u dot v goes on top, and then my square root of 5 times my square root of 10 goes on bottom. I take my cosine inverse of those things, and we get 45 degrees. Now, something just to note. Now, I wouldn't make you like write this out, but just in case you were curious as to like why we get an exact number there, notice what is the square root of 5 times the square root of 10?
5 squared is 2.
Yes, you gotta get the square root of 50, which is also 5 square roots of 2. And what is 5 divided by 5?
1.
1 divided by the square root of 2 is also just square roots of 2 over 2. And cosine equals square roots of 2 over 2 at 45. That's why we end up with an exact number this time.
When you multiply the two bottom magnitudes together,
Correct.
can you multiply them before you put them in the inverse?
You mean like do square root of 50 on the bottom instead?
Yeah.
That's right. The only thing I would say be careful about is like doing your fraction first and then rounding, because if you round first and then take cosine inverse, it's not going to give you an exact number. That would be the only thing you want to be careful about. Alright. That is all we got for vectors.